Hello. The notion of the experiential learning in AI was suggested almost 30 years ago by Ben Goertzel as a way to have an autonomous agent learning any knowledge from the outer world by its own experience and feedback, received from the environment and inferred by the agent itself. It could be supervised learning with feedback obtained by implicit labels or directions, semi-supervised learning with feedback inferred from rewards and punishments provided by environment or instructor, or self-supervised learning, where the feedback is inferred by an agent itself based on its expectations, grounded on its internal model of the surrounding world. In this talk, we will discuss how the unified cognitive architecture based on these premises can potentially help future autonomous artificial agents to learn faster, prevent catastrophic forgetting, make their models and behavior interpretable, transparent, and auditable by humans, and make that all cheaper. We assume that so-called hybrid neurosymbolic architecture make it possible to perform intelligent activity in any of the two different models or representations, in either latent associative networks such as DNNs and transformers, or interpretable knowledge hypergraphs with probabilistic weightings of the symbolic logic assertions. The former one may be associated with Kahneman's System 1, and the latter can be considered as a System 2. We have presented this concept on AGI conference 5 years ago. And the last year work by Pedro Dominguez has shown it is practically possible as long as any system of symbolic logic, as well as any modern neural network architecture, may be expressed in what he calls tensor logic language. Respectively, any world model may be reinterpreted as either hierarchical hypergraph with labeled or unlabeled nodes or edges, or a distributed sparse representation in some latent tensor space with respective topology. And we assume, given the possibility of formalism unifying both worlds, such as tensor logic language, transformation and transition of the two models in the mind of an agent is possible. Interestingly, the same structure of a knowledge in such tensor space or a hypergraph may provide different options for inference performance and possibility of lifelong learning. On one hand, if we keep the knowledge in a network as numbers on the edges corresponding to learned parameters in the model or trained parameters, downsampling these numbers and pruning of a network down to 8, 4, and 2 bits ends up with a Boolean 1-bit parameters corresponding to an old good logical network. On the other hand, if we associate each point in the tensor space of an element of a hypergraph with compound truth value accordingly to P1 and Ben Goertzel, or we keep complete evidence log or counts for each point in space, we may eliminate possibility of catastrophic forgetting happening upon perception of a new evidence. So the new evidence that doesn't override the existing weights or parameters, it just adds the evidence counts or probability distribution, which can be used to recompute the truth value or probability. This kind of conceptual design may be implemented in a technical architecture of an artificial psyche as an operating system of some artificial agent, as presented in our work on Neuroinformatics conference last year. The psyche, as an internal world of an agent, consists of space of dynamically changing states built on transient values of state variables corresponding to agent perceptions of the outer world, satisfaction of its current needs or goals, and confirmations of the actions directed toward the world in order to satisfy these needs and achieve the goals. And within this space, there is a decision-making system, which is intelligence. And it can be either subconsciousness, corresponding to Kahneman's System 1, and potentially implemented as a sort of as a symbolic associative neural network of any architecture, or it can be consciousness such as a reasoning system of System 2 built upon semantic networks or knowledge graphs with some probabilistic inferences. The decision-making system may be neuroassociative or symbolic, or hybrid neurosymbolic. It may look into the history of the past states, use the learned world model to build predictions based on its different possible actions, find the respective future states satisfying the needs and reaching the goals to the greatest extent, and select corresponding actions to execute. The learning function considers the relevant outcomes of the actions in the historical context, and updates utility function values corresponding to transitions from past sequences of states to future sequences of states, along with the evidence count logged into the model corresponding to each transition, so the probabilities can be assessed. The decision-making or inference function in its turn maximizes the combined utility and probability to select the most useful new state with greatest probability. Memory architecture of such system may be fourfold and include the following. First, the episodic long-term memory, hosting full experience log, which is necessary to support complete evidence count, preventing catastrophic forgetting. Still, it may be subject of garbage collection or low evidence and outdated experiences. The second layer of the memory may be represented as either neuroassociative network model such as DNN or GPT, or a symbolic model in forms of graphs, rules, predicates, or invariant patterns grounded upon underlying precedents in the long-term memory. This layer may be thought as either an approximation of the underlying precedents or index to access them, like it was presented in our work with Evgeny Vityaev a few years ago and presented on the BICA and AGI conferences. Next, the operational context used to frame and guide the decision-making process and the acquisition of the new knowledge may be represented by short-term memory, which corresponds to context window in modern LLM architectures. Finally, the current layer of memory is hosted by attention-focused memory. One can think this how this architecture may be mapped to very recent RAG-based architectures with LLMs. One of the most intuitive practical applications may be process control system, subsystem or device, where an upcoming stream of values of state variables from the field is used to generate downstream of control signals used to keep the controlled environment such as factory, engine, vehicle, or device in a state by required an operator, and or move this device or a system to a expected state. In real industry, in many cases, this kind of control cannot be delegated to non-interpretable solution based on modern neural networks, and it is being conducted either manually or using programmable logic software coded manually and executed by programmable logic controllers. Another example, widely used in reinforcement learning and evaluated in our current work, is a toy virtual environment for OpenAI Gym, Atari breakout game, where the field signals are represented by intensities over GB pixels of a video frame and rewards of or loss of life events from the game simulation, and the control signals are pedal movements left or right in order to control the ball, in order to earn rewards destroying bricks on the opposite wall. In our previous works presented on AGI and the New York Mathematics conferences, we have shown how the same kind of problem, controlling the ball by pedal movements, can be solved with nearly the same success rate by either non-interpretable network models using the variation of Q-learning algorithm and interpretable state transition system based on the framework described earlier. Importantly, the same physical problem was solved with nearly the same success rate in two different kinds of simulations: high-dimensional pixel level observations of the RGB screens and low-dimensional object-level representations or coordinates of the ball and the pedal. In both cases, the learning speed and achieved success rate was the same in terms of the numbers of training epochs. At the same time, while the computational resources of a serial notebook were sufficient to learn the game in real time in case of low-dimensional object-level environment, it turned infeasible to do that in real time for high-dimensional pixel-level environments such as Atari Breakout. In our latest work, we use interpretable dimensionality reduction, transforming raw multidimensional stream of pixel data to coordinates of pixel clusters expectedly associated with the ball and the pedal. In the future work, we expect this kind of transformation specific to particular game to be inferred by representation learning. Moreover, we anticipate this would enable to learn even more low-dimensional space built of relatively horizontal coordinates of the ball and the racket. It made it possible under certain random seeds to outperform average human expert player after playing 700 games, outperform average level of DQN player after 4,000 games, and exceed the best deep Q player after 2,000 games. And occasionally we were able to reach the top score of 864, known for the Atari breakout environment. Unfortunately, most of the random seeds we were not, for most of the random seeds we were able only to approach the human level. If measure the learning success by number of processed video frames, we found that our runs with different random seeds present steeper learning curve. So given the most 4 million frames, we reached the highest average score, almost 200, while DQN and Rainbow QN algorithms reached 170 and 175 at 50 million frames and 200 million frames respectively. So we can speculate that we can learn faster. The next landmarks on our roadmap are to make the learning more stable, implement an environment agnostic dimensionality reduction, and test it in multiple environments. Make it possible to split the space of states into subspaces corresponding to multiple concurrent activities, and move to practical applications such as real-world control systems, such as industrial automation of smart home, for instance, where hierarchically dependent subspaces of states may exist. Another challenging task is extraction of programmable logic comprehensible and adjustable by humans from the state transition graph models by means of extended version of supercompilation approach. For instance, application of such solution in an industrial automation environment may take place at either lower level of industrial controllers, learning patterns from their operations driven by programmable logic, and raising alerts in case if operation goes out of control against the patterns. Or it can be implemented at upper layer of human-machine interface, where each solution may also generate alerts in case if unexpected situations, or provide timely recommendations to human operators if they are getting late with their responses. Thank you for attention. The full-scale representation of our work can be found in recording of the workshop of AGI in Russian community, accessed from this QR code. And respectively, there is a latest paper that that can be found on archive as after presentation on the Neuroinformatics conference. Thank you.